Okay, let us start. I believe that some of you have not seen the previous recording. So anyway, I'll just proceed. So today's topic is that the equivalence between Euclidean and Minkowski field theories. The Euclidean field theories is based on R4 with the usual Euclidean metric, and we will show that we are able to pass from the Euclidean field theories to the Minkowski field theories, which are the more realistic version of the models they explains the nature. So let us see. Quantum fields, they are operator value distributions, so they are not very easy to manipulate. So authors from Weitman proposed a hierarchy of functions called the Weitman functions, from which we may reconstruct the quantum fields and the underlying Hilbert space. In this presentation, we only deal with a scalar field theory with a single scalar field. Generalizations to theories containing arbitrary fields like vector fields, Dirac spinors are not conceptual but only technical, and they will be omitted for brevity. So let us see what Weitman functions are. They are a sequence of temporal distributions on the Schwartz space for each natural number n, and they are called Weitman functions if the following properties are satisfied. The first is cluster decomposition property. The second is relativistic transformation law. The third is spectral conditions. Fourth is hermiticity. And fifth is local commutativity conditions. And the last is positive definite conditions. We will explain in detail what each of these properties is in the next slide. First, the cluster decomposition means that, so I believe that some of you do not know what is a space-like vector means. It just means that this vector points to a space not in the space-time that is not causally connected to the origin. Like even the light cannot convey the information from the origin to this space-time point A. And it is the cluster decomposition property means that if A is a space-like 4 vector, then as lambda goes to infinity, this Weitman function decouples in the sense of temporal distributions, meaning that in the Weierstrass topology of temporal distributions. And the relativistic transformation law in the context of scalar field theory means that the Weitman functions are invariant under the restricted Poincare group. Also, I'm employing the informal language of distributions. So actually there must be test functions in each of these arguments. However, I'm just omitting this and I'm treating the Weitman functions as ordinary functions, even if they are distributions. And spectral conditions is that the Fourier transform of each Weitman function is supported in the n-fold product of the forward light cone. Again, the forward light cone is just the region in the space-time that is contained by the trace of the light. And hermiticity is straightforward. And next, local commutativity means that we can flip the argument if these arguments are space-like separated. And lastly, the positive definite conditions means that essentially the Weitman function satisfy this kind of positive definite as infinite dimensional matrices for any finite sequences of test functions. And the utility of the Weitman functions is in the reconstruction theorem. It's a well-known theorem that is contained in the classic book PCT, Spin, Statistics, and all that given a sequence of Weitman functions, there exists a scalar field theory that is unique of the unitary equivalence, such that for each n, White function is the vacuum expectation value of the scalar fields. Here, omega is the vacuum, and phi is the scalar field of the theory. So phi is the operator value distribution, and we are calculating the white function as the vacuum expectation value of the scalar fields. Thus, instead of esoteric operator value distributions, we may work with ordinary temporal distributions, which may have certain properties, in order to construct a quantum field theory. That is the punchline of the reconstruction theorem. However, as stated in the previous talk, it is even easier to work in the Euclidean space because the Minkowski metric is not positive definite, and on the other hand, the Euclidean metric is positive definite and has much better properties. So the constructive field theorists came up with another reconstruction theorem that starts from the Euclidean space and yields Weitman functions. This is the content of the two classic papers named Axioms for Euclidean Green's Functions 1 and 2, published by Osterwalder and Schroeder in mid-1970s. So let's investigate the content. Let Sn be a sequence of temporal distributions, and they are called the Schwinger functions or the Euclidean Green's functions if the following 7 properties are satisfied. The main result of the two papers is that if we construct Schwinger functions that satisfy these 7 properties in the Euclidean space, then there exists a unique sequence of Weitman functions that are the boundary values of analytic functions, such that these analytic functions satisfy this relation. In other words, in a more concise terms, we are able to analytically continue the Schwinger functions into Weitman functions in the time direction with respect to the time component. So these are all just technical issues. So let us investigate. First, the Schwinger functions are supported on S on a specific subspace of the short space, and this subspace is defined as the space of functions, short functions that vanishes, and its all partial derivatives also vanish if any of the arguments coincide. So we are saying that a Schwinger function must be supported in this specific subspace, and also the Euclidean covariance is very much the same as the relativistic covariance. So I have just omitted this statement. We just have to replace the restricted Poincare group with the Euclidean group. And third, the reflection positivity. It is one of the key properties of the Schwinger functions. It is that let us define another subspace of the short space as a subspace that is supported in the non-negative time component. Also define the time reflection as theta. Then the Schwinger functions must satisfy these positive definite conditions. This is called the reflection positivity. Okay, in this case, I use a more formal language of distributions by using the test functions, because this property is one of the key properties for a Schwinger function and must be stated precisely.
Can I ask you, so is this related to Wick rotation and things like that?
Yes, exactly.
So I was wondering if you could explain that a bit to me, because it's a point I've heard about it, but I was always confused about it. So could you, and maybe you talked about it last time, so I'm sorry if that's the case, but could you explain what Wick rotation does and how it's used?
weak rotation is essentially the rotation of the time axis from the real axis to the imaginary axis, and it is essentially the analytic continuation of from the Minkowski of the Whiteman functions and the Schwinger functions as this. You change from real time to imaginary time, and
so
you get
if you do this formally in the heat equation, you get the
yes,
Schrodinger equation, right?
yes,
So that's something that I've never quite understood in the sense that the behavior of solutions of Schrodinger as compared to heat are very different, right? So Schrodinger preserves probability and heat equation decays. So in what sense do you connect those two equations by Wick rotation?
yes. The relation between the Schrodinger equation and the heat equation is exactly the same as the relation between the Whiteman functions and the Schwinger functions. So how to explain?
I guess what I'm asking is, my rough understanding is that you Wick rotate to get a Euclidean. So if I just think of linear Schrodinger equation and
Okay.
I do a Wick rotation, I guess the associated Euclidean field theory would be the heat equation.
Yes.
Maybe yeah, okay. But now you want to make statement about the Euclidean field theory, which is just the heat equation,
Yes.
and presumably say something about the original theory, which was Schrodinger. Is that you want to rotate back or say something about the original field theory, right?
Yeah. Yes.
So my question is, how do you do that if the behavior of the solutions of the heat equation is so much? I mean, there's something I don't understand about going back and forth in these descriptions.
Yes, it is true that the solution of the heat equation decays and the Schrodinger equation just oscillates. That is why we prefer heat equation, because it decays and it shows much better, it exhibits much better asymptotic behavior. However, if we put some restrictions on the solution of heat equations, such as a property that is analogous to reflection positivity or symmetry that I'll explain, or linear growth conditions or cluster decomposition, then I anticipate that the proof that is analogous to the one presented in these papers, and that these proofs are very complicated. They are like they use a lot of functional analysis and so on. Anyway, it is possible to recover the solution of the Schrodinger equation. That is the truth. If we with some restrictions on the solution of the heat equation, that may look like magic to someone who has not seen the proof of the equivalence between Euclidean and Minkowski field theories, but
it's clearly not true for all data, right? So it's some subclass. Yeah.
Yes,
you're saying it's some subclass.
Yes.
Mm-hmm.
So essentially, this reflection positivity.
What does that mean?
This property, even if you reflect with respect to the time axis, you get a positive definite Schwinger functions. This is related to the positive definite conditions of the Whiteman functions, and so on. So with all these properties, you can reconstruct the Whiteman functions from the Schwinger functions with this formula.
Yeah, I don't know what but so reflection positivity as a statement about solutions of the heat equation. What is it saying? Is there an easy way to say what it says?
Actually, I do not immediately see how to formulate reflection positivity for heat equations, but for Schwinger functions, they are formulated as this. And I'll think about the relation between. I'll think about how to formulate reflection positivity for the heat equation and the Schrodinger equation, and we'll tell
Yeah,
you.
that would be great. I would really like to know, in what sense is there a correspondence between solutions of heat equation and Schrodinger? You know,
Okay.
yeah.
And symmetry is that the for any permutation of the arguments, the Schrodinger function is invariant, and hermiticity is like this. You for any permutation and for reflection positivity, you just get the conjugate value of the Schrodinger functions. And in fact, hermiticity is not listed as one of the axioms in the original paper. However, upon doing the research, I also find it necessary to pass from the Euclidean to Minkowski settings. So I include the hermiticity here. And lastly, the cluster decomposition property is very much similar to the Whiteman case. And lastly, there is a linear growth condition. Paper 1 does not present this formula 13th, but in paper 2, the authors say that paper 1 contains an error in it. They claim that we need a growth restriction on the Schrodinger functions Sn in order to analytically continue them with respect to one time variable at each step to Whiteman functions. The linear growth condition in its simplest form is given as this, where sigma n is a sequence of factorial growth and fi, each fi belongs to a short space based on R4, and S is just a fixed natural number. And this is the semi-norm in the freshest space, short space. So this linear growth condition is something that Professor Glim pointed out as very unnatural, but according to the paper, it is necessary. It must be included in order to pass from the Euclidean setting to the Minkowski setting. So I also believe that for the solution of a heat equation to pass to the solution of the Schrodinger equation, it must analytically continue with respect to time variable, and in order to do that, it must be restricted in its growth for some constant, or at least some growth. At least it must be put some growth limit. That is what I expect.
Wait, so could you say that again? You expect that solutions to the heat equation with such and such property related to growth are connected to Schrodinger?
Yes, I expect that the solution of the heat equation with some linear growth restrictions can be
bounded above linearly as you go to infinity.
Yes, can be analytically continued. In its time variable to emit. That is, it can be weak rotated, or it can be extended to expanded with respect to the time variable to analytic functions, and then go to the solution of the Schrodinger equations. That's what I expect.
But the solution of the heat equation in that context will decay in time, right?
Yes.
And so now you have a function defined on, say, R cross R, time and space.
Yes.
Which is going to zero as you go to large time. But Schrodinger, so if you take that function and you Wick rotate back, how will you reproduce the behavior of Schrodinger, which preserves the norm square?
Could you say it again?
I'm just saying the Schrodinger equation preserves the the probability, right?
Yes.
But at long time, the heat equation is decaying. So
Yes.
how do you reconstruct by Wick rotating back a solution of Schrodinger that preserves the probability if the heat equation solution is going to 0?
Let me show my understanding. So it's almost done. So let me show my let me just use a whiteboard and show my understanding. Let F be the solution of the heat equation. Let Ftx be the solution of the heat equation. And I believe that under certain conditions, F can become analytic with respect to time variable. That is, we can extend, we can have Z as, and F is analytic with respect to time.
Mm-hmm.
And we can restrict this Z to purely imaginary line, IT. Then FIT, oh, oops, sorry. This is the solution of the Schrodinger equation. That's what I understand. How I understand.
Yeah.
I think what Minchun is trying to say is that decaying in the real axis doesn't mean that it's decaying in the purely imaginary axis.
Yes, that's what I mean.
So that's not a contradiction.
So could you explain it? Like how do I? So I have let's say I have the heat equation, and I start with initial data, maybe complex, but it's linear, so the real and complex parts decouple, and there are linear equations for those. And now I have an all-time defined field for each one as a function of space and time.
Yes.
And now I just take that function and I insert into its time argument the imaginary number I times real number t.
Yes.
And that is supposed to solve Schrodinger?
Yes. Yes, right. Under certain conditions.
So maybe I'm being stupid, but isn't this just like the real exponential e to the minus t decays, but e to the it doesn't decay?
Yeah, that's exactly
true,
what
yeah.
it is. Yes.
Yes, as somebody pointed out, in the real axis, in the real time, there is exponential decay. But if we rotate to the imaginary line, there is just there can be just oscillation. So there's no contradiction. And we can rotate from the real axis to imaginary axis under certain conditions. And that conditions contain the linear growth condition for the solution, I believe.
Okay.
So our current research with Professor Klemm is that, as with the Whiteman axioms, the notion of Schrodinger, Whiteman functions, and the reconstruction theorems do not encompass gauge theories and gauge symmetries. So our very first paper, in the series of papers we are writing, and our first paper is being written by me mainly, is to extend these concepts and the theorems to include general gauge theories by completing this very first paper, we anticipate to thoroughly figure out the goals we need to attain and the tools we must use in this process. So this is the current situation we are in and the background information I can provide. And I hope that Sasha to be here, but I'll show anyway. I believe that many of you are familiar with fluid dynamics, so I'll present what I know about what I have done about the fluid dynamics. But please be aware that I'm not really conversant in fluid dynamics, so I may not be able to answer many of your questions, even if you have. So this is my formulation. So here, I believe that many of you are not really familiar with the summation convention, right? Meaning that if there are two upper indices and if there is upper index and there is a lower index, then they are summed. So this is just a convention, and you don't have to really think about it anyway. So let us assume that A mu, and mu is the index that labels the space-time components. Mu can have the values 0 and 1 to 3. 0 meaning the temporal component, 1 to 3 meaning the spatial component. So A mu is a 4 vector in R4. And we have a Lagrangian, and I believe you're familiar with Lagrangian. And we impose a local U1 symmetry. That is, lambda is a smooth function, and we assume that A and phi are actually cross sections on the U1 bundle over the base space R4, and they transform as this. And under the transformations 2 and 3, we can see that L is invariant because the definition of F, I have not present the definition of F, because the definition of F is, okay, let's see. Because definition of F is this. This is the definition of F.
Sorry, could you zoom in on the text a bit? It's a little small for me.
Oh, I don't know how to zoom the text.
Just that plus sign with the circle around it. Like right at the top center of your page.
Okay.
That's much better. Thank you.
So this is the definition of F. And under the gauge transformation 2, under transformation 2, which is called the U1 gauge transformation, you don't have to care about the name. Anyway, under the transformation 2, you can clearly see that F is invariant because the partial derivatives commute. Also, it is well known that this.
So is G a constant? What is G?
Yes, G is just a constant. Oh, sorry about not clarifying. G is a constant, just a constant.
Okay.
So with the Lagrangian, we can calculate the Euler-Lagrange equation as the equation of motion. And the correct calculation gives this. Here, dagger is just the complex conjugate. Physicists use this this notation a lot. So dagger is just a complex conjugate, and we obtain this number equation 4 as the equation of motion. And you can easily check that the right-hand side of 4 is invariant under 2 and 3. It's just a simple calculation. We denote right-hand side as a 4 current density J nu, then which automatically satisfies the continuity equation. This actually, this equation is, I believe that all of you are familiar with the continuity equation, and it can be very compactly written using the Einstein summation convention, meaning that mu equal to 0 is just the time derivative, and mu equal to 1 to 3 are the spatial derivatives, and they are all summed together with respect to the Minkowski metric. So number 5 just means that the time derivative of J is equal to the divergence of the spatial components of J.
Could you say why is 3 why is L invariant under 3?
Oh, that requires some calculations, but okay.
Isn't it simply complex conjugate giving you e to the negative I lambda, and then if you multiply them, it cancels?
Yes,
Aren't you taking a derivative?
phi is just phi transforms as the transforms as 3, and it is very well known that the covariant derivative of phi transforms the same as phi. It has been constructed, the covariant derivative capital D mu has been constructed in order to make this D mu phi transform exactly the same as the formula 3.
Okay, because of the thing in 2. Yeah, I see.
Yes. So
Mhm.
this complex conjugate cancels out with the original.
Okay, no, I understand. I just didn't know the definition of D. Yeah.
Yes.
Yeah.
So this is the equation of motion, whose right hand side we denote as J nu. For J equal to nu, the equation of motion becomes this. Where F0 is F10, F20, F30, and it is by definition equal to this. So we obtain the formula 7, and it is just all matter of calculations. And after all manipulations, we obtain formula 10, where J tilde is just some messy function that is to be named as external source. That is to be interpreted as the external source for the fluid. And now, so for user,
why is there I'm a little confused. So why are you saying an external source? You're Lagrangian. So you have a Lagrangian, you're writing down the Euler-Lagrange equations, is that right? Or you doing something else? But your Lagrangian encodes an external force?
Yes, this F and A will be interpreted as the velocity field of the fluid, and this phi will be interpreted as the external matter source, external force, external source of force.
Okay.
So we obtain the formula 10. And
Here, if your Lagrangian doesn't have your phi, you just get the Maxwell's equation. Is that right?
right,
And then what does the phi encode?
the external phi is a scalar field, and it encodes the external source of energy or force. It encodes a stirring force according to Professor Gleim.
But according to Daniel's interpretation, if it's not there,
just
you
gives
get a
you
linear
the,
theory.
It gives you the electromagnetic theory.
Okay, so maybe let's see how you conclude, and maybe it'll be more clear.
What do you mean by linear theory?
Well, if the phi is not there, then that's the action for
Yes,
electromagnetic theory.
that is correct.
That's linear theory, right?
Yeah.
Yes, that is correct. So we interpret A mu as the force velocity field for a fluid, and phi as another matter field interacting with the fluid, or the external source of energy or stirring force. So we interpret A mu as the velocity field of the fluid in the relativistic sense. I believe that some of you may not be familiar with special relativity, but anyways, because gauge theories or quantum field theories, and quantum field theory is based on special relativity, I first have to use special relativity, and then I'll pass to the non-relativistic limit, in which we get the equation of motion for just ordinary fluid. So we interpret A mu as the velocity field, and this capital V is just some internal potential, such as the pressure of the fluid, and so on. Then we substitute formula 13 into formula 10. We substitute formula 13 into formula 10, and after calculations, we obtain this formula 14. And after we pass to the non-relativistic limit, in which V becomes really small compared to the speed of light, which has been set to be 1, so that this gamma is almost equal to 1, we obtain this equation. "14 reduces to 16.
So, but again, with what Daniel said, if you set the phi in your action to be 0,
Yes.
right, then the equations that should come out are Maxwell's equations. Is that, you agree, or?
In order to get the Maxwell equation, we have to we need a different interpretation of A mu with phi 0.
Well, I thought that the point was that the Maxwell equation, that A mu was the vector potential in the usual E&M formulation. The Euler-Lagrange equations in that case gave you just Maxwell's equations, where A mu is the vector potential.
Yes, that's conventional physics. And
Yeah.
in this case, instead of interpreting A mu as the vector potential for electromagnetic field, we interpret A mu as the velocity field for the fluid.
Yeah, but I'm saying that the interpretation or otherwise, I mean, you get some equations where A mu plays the role of the vector potential in electromagnetism.
Yes.
There's no freedom in that, right? Once you I mean, this is instead of interpretation, it's just that's what it has to be, unless I misunderstood. So are you claiming there's a mapping between fluid dynamics and electromagnetism?
Yes.
What do you mean by that?
It is that okay. Let
In
me
like
show
the
you.
in the first paper, right? There's that table that shows you what the terms correspond to.
Yes.
Is that what you're going to bring up? Yeah.
Daniel, do you agree with what I'm saying, or do you understand something different?
I don't know. It's I'm not too sure what it means for phi to just go away. I was actually more worried about yeah, this small phi to capital phi.
So there is this kind of correspondence holds between electromagnetism and fluid dynamics.
What's small l on the right side?
Lamb vector. It is the cross product of the velocity field and vorticity.
I see. Does the capital phi scalar potential have anything to do with the small v? Like, are you assuming that this is a potential flow? What do you mean by scalar potential?
Oh, here, sorry about the use of different notations.
Oh, it's
Sorry,
here. It says
what
here.
is
Okay.
capital V? This is what is capital V? Somehow
What is
related to the pressure or something?
Oh, I see.
Yes.
Okay.
I think capital V is the potential energy, isn't it?
It is potential energy, and according to the paper, it typically represents pressure divided by density, mass density.
Is this just rewriting the fluid equations? I mean, they're still fully nonlinear. It's just the sources are going to involve. I mean, I guess you can always rewrite things to look like this, but the J will be quite complicated, I guess.
Right.
But it's just a rewriting of the usual equation.
Yes, but the point is that we rewrote the the fluid dynamics in terms of a gauge theory, and if we know that a gauge theory exists, then we may conclude that the solution of the fluid dynamics also exists.
Gauge theory exists. What do you?
Yeah, I think I have somewhat. What does it mean to exist? You just impose those constraints in your equation and the thing you started with.
I mean that the solution of the equation exists,
I'm
If-
not sure you, yeah, okay, sorry. Oh, go on, sorry, I was cutting you off.
Yes,
I
I
wasn't
meant
clear
that.
what,
I meant that we just what we have done is to rewrite the equation of fluid dynamics in terms of gauge theories, and we are currently constructing rigorously the gauge Lagrangian I just showed. So if this Lagrangian exists in a rigorous mathematical sense, then how do I explain? Sorry, I am not really able to convey the thoughts I have, but the theory exists. If the theory exists, if the theory is constructed, then the solution of the Navier-Stokes equation is shown to exist. That's what we are trying to do.
okay. So it's a statement, if you have a Lagrangian, and that's invariant under some given transformations, that is what it means for a gauge theory to exist. Is that what that phrase
Yeah.
means? Okay,
Yes.
and so once you have that, you're claiming that the equations of motion always have a solution?
Oh, in fact, it's more than that. It's more than just this Lagrangian is an interacting Lagrangian, so we have to construct the interacting fields, A mu and phi, and that if we succeed and write down the Lagrangian in terms of these interacting fields, then we succeed in constructing a non-trivial theory described by this Lagrangian. That's what we are trying to do, and constructing this interacting field is non-trivial job.
And what's the theorem that says that you'll always have a solution? I didn't quite understand the reasoning behind that. That seems like a very powerful statement, that if you just construct this object, you're always guaranteed solution. Can you unpack that?
The interacting fields themselves are solutions of the gauge theories.
So there are various action principles for fluid equations. Could you say what makes the one you wrote down different? I mean, how do you? I mean, for one, I guess the A plays the role of the velocity, and your action is quadratic in derivatives of A, which is quite different from the usual fluid actions, which are, you know, with A itself, not derivatives of A. So maybe you could comment on that difference.
Yes, by using the second derivative of A, using the quadratic term of A, I'm able to impose some symmetry on the Lagrangian, and that is called the gauge symmetry, and that is called the gauge theory. And it is a framework that is very well known to quantum field theory.
So is the fact that your action, some derivatives of the, I mean, is your action preserved by solutions of the equation of motion? Is that true of your action?
Yes.
So are you claiming that there's some invariant quantity involving derivatives of the fluid velocity for the Euler equation? If so, it would be nice to write it down directly and check that solutions of, say, the Euler equation preserve that combination of derivatives.
Hmm. I am sorry about not being able to explain more in detail, but
So I'm just saying that in 3 dimensions, like, so the f square term there looks to
yes.
me like I don't know, like the vorticity square, something like that, if I interpret a as the velocity. But that quantity is not preserved in 3 dimensions, for example. So maybe there's something going on with the other term. I guess I don't really understand the meaning of the action. Is it something that's really preserved by the dynamics? And if so, what is that quantity in terms of the solution? Is it?
It's for now. For now, we just judge that it's just a device that gives the equation of motion, nothing more than that.
But is it preserved by solutions of the equation of motion?
What do you mean by preserved? Like it's
Like, so that Lagrangian is a combination of the observables, the velocity and so on of the theory, right? And
yes,
it has a certain value at time 0, given by what that combination is in terms of the initial data. And then
yes,
by preserved, I simply mean that over time, whatever that value is doesn't change. So
yes, it does change.
it does change, okay.
So maybe all the gauge theory is as you said, just a mechanism to derive the equations of motion, but it doesn't actually shed light directly onto those equations of motion. It just is a way for you to sort of write down a Lagrangian and then push through to get, fluid dynamic equations. Is that right? Because I think maybe what I'm trying to do is make a connection between the sort of gauge theory that you've been talking about in this QFT that you've been talking about to fluid dynamics, but it doesn't seem like that connection is so clear other than, you can write down some Lagrangian and then, do some calculations to push out a fluid dynamics equation. Is
Yes,
that
for now,
okay?
that is all.
Is there a reason why on the right side, on A corresponding to V, you have 2 arrows? V has 2 arrows on the top.
Oh, I think it's just a typo.
Typo? Okay. And
Can you show? Yeah, go ahead, sorry.
is this correspondence just some kind of weak one, or does it have a really exact correspondence, such as the left side satisfies the Maxwell's equation? So if you write that for the right side, you get an equation for the values and the variables on the right side? I guess not.
I
think
guess
it
so.
is. I think it is, but it's a sort of just rewriting the usual equation. If you go to where they write equations, can you go up or something? Where do they write the equations for these? Right here. Yeah.
Oh, I see.
These equations, if you look at what J is, maybe J is
Mhm.
on the previous page.
Mhm.
I think it's just taking the usual equations and putting some terms on one side and some terms on the other side.
I see. But in the second paper that you showed today, you had A as some complex formula for V. I think equation 13 in the second paper. Can you show
Oh.
us the second paper? Or the presentation PPT that you showed? Yeah, this one, equation 13. You have A defined as something complicated. It's not, A is not equal to V. It's A is defined as some complicated form of V and phi.
Oh,
Is this A totally unrelated to the A on the other slide?
actually, this paper just worked in a non-relativistic framework, and there's another paper that works in the relativistic framework. I combined both of them. So let me show you the other paper.
Okay. So even here, A is V squared, norm of V squared.
I think the spatial components of A are like V.
Yes.
Oh, okay. And then the time one is like the energy. That's what's
Yeah.
The
happening.
kinetic energy. And I think in this paper, they missed the pressure term in the time component. So I added the pressure term by adding the capital V.
I don't really understand this concept of adding things or interpreting things. I mean, doesn't that have to come from when you, at the beginning, you say once and for all what the fields are and the action are, and then you derive equations of motion from Euler-Lagrange equation? I mean, what do you mean by adding? I'm just a bit confused by that.
If there's a fluid, then it must have its internal pressure, right?
I agree with that, but I thought there was some formulation. So at the very beginning, you have this action involving A, and at a certain point, you declare A has a certain form.
Yes.
So your claim is, I mean, what determines that potential V? And I mean, are you saying that is a general form for A?
Yes.
But then why don't they have that term here? I mean, why is it a general form and here it's a different A? I mean, also, I mean, why did those relativistic factors show up? I guess don't quite understand.
Because I thought these papers contain some errors. So that's why I added those terms, and I practically made some corrections myself.
So if you have a solution to the electromagnetic theory, then
Yes.
that's going to give you a solution to the relativistic Navier-Stokes equation. Is that right?
Yes.
But it can't. I mean, but electromagnetic theory with some complicated sources, right? It's not. It's not like just the usual unforced E and M theory. It can't be. That's a linear theory.
Okay.
So it's just a rewriting of the equations, and you just take them and you put one term on one side, the other term on the other side. That's
Mhm.
it. I mean, I don't see
What is the
what.
source? Sorry, what is the
So
source
if you,
here in EM?
yeah, if you go to the equations where they look like electromagnetism in one of these papers, I don't know. I think it was in the other version of this paper.
Yeah,
The other
the
paper.
J's.
Yeah, if you scroll up just a little bit to so we can see both. Yeah, okay. So
Yeah,
I mean, sure, you know,
I
you can
see.
write things like this if you want to. I don't see what it tells you beyond what the original equation tells you.
Well, I think if you write it, if I understand correctly, if you write it this way, you get these symmetries where you can do these substitutions continuously. Isn't that what that buys you?
I don't even know what that means. I mean, I don't know what symmetries. mean-
In his the corrected revisions, if you go
Yeah, but
back to, okay,
I just don't. I mean, here you take the Euler equation and you put one term on one side, the other term on the other side, right? That's what these are. So, I mean, for example, equation 16 is just a vector calculus identity. Equation
Right.
15 is just the curl of the velocity equation.
Mhm.
You know, all of these are just basic consequences of the equations.
Mhm.
Now, it does look like E&M in the sense that you have this correspondence, but you have sources and currents that are highly nonlinear and so on. I don't understand what the, you know, what it gets. So, okay, it's phrased like this. Now what can you say?
We construct. Yes, I keep repeating the same word. We construct the Lagrangian with the terms v with the terms a and phi that yields these equations of motion.
So there are many actions that yield the equations of motion for fluids, right? There are many of them. So what's the upshot of constructing an action that does that? What else do you learn beyond that there is an action that gives you those equations? There are many such, and probably you have one too. Now, what can you use that to say about the fluid? I'm not trying to say there isn't something. I just don't. I don't yet understand. This is what I'm trying to understand.
If there's an action that gives the equation of motion, and actually by saying that there's an action that gives this equation of motion, I'm also implying that this action also has a solution for this equation of motion. That's in the context of quantum field theory.
I don't really know.
I think if equation 13 that you see on the screen, if the right side has a better interpretation in terms of physics, we might be able to get something. Does
Unfortunately, the
side
right-hand side is not even well defined in terms of mathematics because, for example, the second term there is the curl of a scalar. I mean, is not even interpretable the way it's written. So I imagine there's typos, but
that's right. Huh.
in the Lagrangian you wrote down, where's the J?
the
So
J
if you
is
go,
the 13. Oh, that J.
no,
Oh,
no,
different
no.
J.
Okay, okay. So can you go back to your corrections? I think is what it's called. Okay. To the very top. Okay, okay. So these are different. I see.
So
Where
is
are
10 supposed to be the Euler equation actually? Or is that correct or?
Yes.
And if I want to think of no forces, I can just set the J tilde equal to 0. Is that right?
Yes. By
so J
setting
tilde? Oh,
okay, by setting J tilde equal to 0, that is equivalent to setting phi, this matter field phi equal to 0.
Is that d by dt? Is that supposed to be like the material derivative, or is it?
It's covariant. It's not material derivative. It's covariant. It's called covariant derivative, and it's a concept that appears in the gauge theories.
Does it correspond to the material derivative? I mean, is it dt plus, is it the covariant derivative in the direction of A? Or what is it?
You mean this one?
No, in that equation 10, you had a partial t. It's the first. Oh, so that gradient is supposed to be if I were to write that in vector calculus notation, would it be A vector dot gradient A0? Or I guess I'm confused about the notation of that second term.
Oh,
Oh,
A0 is just one component, one ordinary
Yeah.
function.
Spatial gradient, isn't it?
Yes.
It's a space.
Yes.
Okay.
But with J equals 0, this equation is linear, right? So I'm trying to understand how this equation corresponds to a fluid equation.
I think what's happening is that this approach and the previous one is different. That this one that we're seeing has nonlinearity in A, so A is like square of V and all that, right?
Well, but in the non-relativistic case, the A vector is just linear in V. Gamma goes to 1.
Oh, I see. So the first
So-
one's the time
Yeah,
energy,
the first
and the
component
second one.
is
I
the-
see.
So looking at
So
equation
J
10.
has the nonlinear part. But I keep
No,
looking at
but J is 0, right? J is just external forces, I think, is the claim. I think the claim was that the J tilde in equation 10 is 0 if the external force is 0. Is that true or no?
Yes. Right.
Okay. So if
But
that's
then-
true, the left-hand side is a linear equation.
Yes.
Is that true or no?
Linear equation with respect to A.
Yeah, exactly. And A is like V. A in the non-relativistic case,
Right.
A is V.
But A0 is the square of V.
That's fine, but that's a pressure gradient. So that's not the nonlinearity of the fluid. So that's different, right? So you could group, depending on what type of fluid you're studying, incompressible, compressible, there are terms that could be potential forces. You could call them pressure. But the fluid nonlinearity is in the other term. It's not a potential force. So looking at equation 10, the first term looks to me linear in A.
Yes.
Unless then this is not a fluid equation. I mean, can you go down to where you did the substitution? Maybe it's there. So here, yeah, this is not. There's nothing to me that looks to me like the usual fluid equation here.
What about the gradient of V squared?
That's a potential. That's a potential force, right?
Oh, V square. There's two V. The capital V is the potential, and V square is the
Sure, but that's a gradient. It's a potential force in that sense. So you see in equation 16, that is not the fluid equation, right? Because you're using a vector calculus identity to write gradient v squared as two different nonlinear terms, v dot grad v and v cross omega. The real fluid equation would be where you don't have the first term on the right-hand side.
Right.
So this is like just a rewriting of the gradient force, this is not the Euler equation.
That's correct.
So it's off just by this negative v cross omega.
You can
If you
view it
drop
that
the v
way.
cross
If you drop,
omega,
yeah,
then it's the correct equation.
Mhm.
Assuming that you have some justification for saying what v is, so maybe enforcing incompressibility or whatever. But
So without this term, it is
Yeah.
the fluid equation.
Yeah.
Okay, I see. Okay, I think I have to make major corrections. Thank you for your comment.
sure.
Min in the beginning, where you introduce these symmetries. So I just don't know enough gauge theory, but what does it mean that this Lagrangian, has these symmetries? What does it mean for it to be invariant?
If you substitute these values into the Lagrangian,
Nothing changed. Yeah, nothing changes.
changes.
I see. And so when you write down your equations of motion, does it inherit anything, like any
Yes.
of these symmetries? Okay,
Yes.
so can you show us that? Okay.
This is the equation of motion.
Okay, and so it will also have the same, you put these, you substitute these terms and okay, nothing changes. And does the Euler equation, or I guess the Euler equation as you derived it, should it also have these symmetries?
Yes.
So, okay, that's interesting. So once you derive your form of the Euler equation, you should be able to basically substitute these terms in. But where are these terms? So in your Euler equation, I don't know where, if you scroll down, I guess, to 10. So what is a mu and what is where does the phi come in? Right, because you're saying that you can substitute those and nothing will change here. But those terms don't even appear in this, if I understand correctly.
Phi is hidden in J tilde. And the left-hand side is invariant under the above transformation for A.
Theo, do you think this could work for two-dimensional fluids or maybe potential flows?
So yeah, same problem in 2D. I see. I don't really understand the whole derivation since a lot of the.
I mean, if you just look at the final equation, equation 16, could that work and say in 2D V cross W might just vanish?
I don't think it vanishes because you can, this is called the Lamb form of the equation. If you write the nonlinearity as V cross W, it won't vanish. It'll reduce to a scalar, the scalar vorticity, the coefficient of the third component times the.
Okay.
Yeah. Potential flows Well, there one has to really think about like boundaries and things like that. If you're also incompressible, because then, because then the velocity is harmonic. I mean, the potential is harmonic. So I don't know. I'd have to. Usually,
Oh,
the way the fluid nonlinearity comes out is because you're imposing a constraint, right? So the usual action is the kinetic energy, but you subject it to the divergence-free condition. Essentially,
if
that's
if the fluid is incompressible, then does this term disappear?
no.
No.
No, it's a crucial term. That is the term in the fluid equation, essentially.
So either the second term on the left side should vanish, or the first term on the right side should vanish, right?
Yeah, I
Am I
think the
understanding?
convention. Yeah, that's right. I
Yeah.
mean, the only difference is there will be, depending on how you choose to write it, there will either be a contribution to the pressure of the form 1/2 v squared or not.
Mhm.
And
Yeah, I don't understand this entire thing completely, but I thought that you would get some nonlinear term if you were applying the covariant derivative to A, because the covariant derivative already has A in it. So I was like equation
but
10, I was hoping that, just like how Theo was saying, I was hoping that equation 10, one of the derivatives were actually covariant derivatives, not just the regular derivatives.
if you look at the action, the original action, if you don't subject it to any constraints, then the action is quadratic in A, right? Those are the F
Right.
the F mu nu is d mu A nu, so it's quadratic in A. I can forget about phi because I don't want to think about external fields. So unless you subject it to a constraint, the field theory should be linear. I don't see why it wouldn't be linear.
Right.
You need to gauge the constraint, as Dennis likes to say. And if you gauge the constraint, then there'll be a nonlinear theory that comes out, and that will be a fluid theory.
I see.
Do the substitutions have a physical meaning? So the phi you said was hidden in this J tilde. Does that, or actually the phis also appear there. So what does it mean physically that it's invariant to the, I guess, the exponential multiplied against it? Right, because at the very top you show that your fluid equation that you derive, right, it should be the case that you can do this and nothing changes. So I'm just wondering, in the fluid, does that have an interpretation like this sort of substitution and nothing changes? I'm just thinking of a
Because
fluid and you're sort of doing something to it and nothing changes.
because we can, by this manipulation, we can impose this condition.
Okay, so you're not actually like rotating the fluid, or you're not actually, you're using this to sort of infer this extra, more physical constraint.
Yes.
I don't quite see how that's, but okay. I guess that's worked out in above.
So I'm a little bit confused because I'm not really familiar. I'm not very much familiar with fluid dynamics. So according to standard fluid dynamics, this term should vanish, right?
No, it shouldn't. It shouldn't vanish in
It should be
equations.
there.
That term should not be there in that equation. Yeah.
Either the second term on the left side should vanish, or should not be there, or the first term on the right side should not be there. It doesn't vanish. Those are they shouldn't be there. Vanishing means that you're satisfying an equation, which is different than saying it shouldn't be there.
Yes, right.
If it vanishes, then actually it satisfies a different equation than Navier-Stokes, so that's another problem.
Okay, I'll try to figure out more then.
I think it has to do with the fact that you're not imposing constraints in your action. I mean, I think you need to impose a constraint to get a nonlinear. I mean, either that or have higher order terms in the action, because if it's a quadratic action, then the equation should be linear in the end.
Okay. Okay, I will think more. So I think it is now a good time to conclude my talk. So thank you all for your very good comments. So that I can recognize my errors. So I thank you very much.
Thanks for the talk, and you should probably get some sleep now. Yeah.
Thanks a lot, Minchul.
Thank you.
Thank you.
Awesome. Thanks.
All right, take care, everybody. And remember, next week, tentatively 5 o'clock for Sasha's talk.
Okay.
All right, have a good week, everybody.